say we want to do this check your understanding problem. So we have a boat that's going north and a river that's running east. So I'm going to start by using that to make my coordinate system. East will be X, north will be Y, and now let's sort of figure out what information they give us. So we've got a boat heading north in still water, and it would be going 4.5 meters per second to the north. So that would be J hat, and that's the velocity of the boat, and it hits a river, and the river is flowing off east at 3 meters per second. East is I hat, the X direction. So that's the velocity of the river. Actually, I'll go ahead and write that up here so I got a little more room. Velocity of the river. And since it's a relative velocity problem, we got to figure out who's measuring the boat and who's measuring the river. Well, the river is measured relative to Earth. So just remember the convention here. That first subscript is who's moving, which is the river. The second subscript is who is observing, which is the Earth here. So it's the river with respect to the Earth. River with respect to the Earth. All right, and then over here, this is the boat. So it would be going due north in still water, but it's on the river. So it must have been bent sort of east. So this must be the boat with respect to the river. The river sees it going due north, but anybody else would see it sort of tilted north and east. Okay, and we want to know what is the velocity of the boat relative to Earth. So again, remember the convention. This is boat with respect to the Earth. This guy is boat, the first subscript, with respect to the river, which is the second subscript. And looking at this, can we find the velocity of the boat from the viewpoint of the Earth? Well, yeah. So if we remember our convention for how we do relative, I'm just going to erase that so I have enough room. How we do relative velocity, the first subscript over here on the left-hand side of the equation is going to be the first subscript also on the right-hand side. And the last subscript on the left-hand side of the equation is going to be the last subscript on the right-hand side. And then the two middle subscripts, they have to be the same thing. So we have boat and Earth, so the remaining object in the problem is the river. So that'll be the fill-in middle subscript. So we see we need the boat from the viewpoint of the river and the river from the viewpoint of the Earth. Happily, those are the two that we've got. So boat with respect to the river, that is 4.5 meters per second in the J hat direction, or north, how we set up the axes. And then the river with respect to Earth, that is 3.0 meters per second in the I hat direction, or east, as we set this up. Of course, usually we put the I hat stuff first. So let's go ahead and rewrite that. And there we go. That would be the velocity of the boat with respect to Earth in component form. So we can go ahead and say, great, we've solved that. Let's check that it makes sense. This is saying our boat is going a little bit east and a little bit north, and that makes sense if the boat's trying to go north, but it hits the river going east. It's going to be going north and east at the same time. Now say we also would like to know the speed. So that will be the magnitude of the boat's velocity with respect to Earth. That'll be the square root of the square of its components. So 3 meters per second squared plus 4.5 meters per second squared. We go ahead and calculate that out. Well, the square root, 3 meters per second squared. The 3 squared will be 9. This will keep the O on just so we can get our sig figs later. Meters squared is meters squared over seconds squared is over seconds squared. 4.5 squared, that's 20 and a little bit extra. 20, 2.5 meters squared and second squared, meters squared over second squared. There we go. Add those guys up. We'll have 29.25 meters squared per second squared, and we can add them because the units are the same for both. Take the square root of that number and we get 5.4. Keep 2 sig figs because we had 2 sig figs in the beginning, and for the addition we were in the tens place. So all of that's good. Now take a look at the units. We have meters squared. We're taking the square roots. That'll be just meters over second squared. Take the square root. That'll be just seconds, and we have the right units for speed. So there's the speed. And then if we would also like to figure out what direction it's going, well, it was going north and east. I guess if we just erase the river here and maybe draw our arrows to scale. So 4.5 meters per second to the north, 3 meters per second to the east. So we'll measure this angle. That'll be east of north because we started north and we pulled it east. And then it looks like, well, we've got, this is our hypotenuse, the full magnitude of the velocity, which is 5.4 meters per second. And we want that angle, so we'd want the opposite over the adjacent. That would be the tangent. So for the angle, that would be tangent of this angle would be opposite 3.0 meters per second over the adjacent 4.5 meters per second. Got the same units on the top and the bottom, so they cancel. And then if we actually want to get the angle, we actually need to do the arctangent, the function which undoes the tangent of 3.0 over 4.5. Plug that into your calculator. We would get, using the correct sig figs, 3.34 degrees. And the direction, again, that would be, let's see if I have just enough room to fit it in, that would be east of north. Because again, if we start from the north, we measure 34 degrees east of that. And that's how you solve a relative velocity problem. The important thing, just make sure that you set up the equation, it follows the rules. First subscript, last subscript, and the middle subscripts are the same, and then you can add or subtract as you need to. But there you go.